Good morning, good afternoon, and good evening, and welcome to our webinar. I'm your host, Chris Rice, Marketing Coordinator at ConnectTech. We're thrilled you could join us. Today, we will learn from the leaders in software, hardware, and vision for building a next-gen autonomous mobile system. After the presentation, we know you'll leave with confidence and be ready to tackle the challenges that you may face when choosing an ideal solution for your project's goals. First, a few housekeeping items. This webinar will be recorded so that you can watch it again later and share what you've learned with your colleagues. After this webinar, we're going to have 15 minutes of live Q&A, so please submit your questions during the presentation and we'll try our best to address them all. Amulya Vishwanath is a Principal Product Marketing Manager for Robotics and AI at Nvidia. Amulya drives go-to markets for developer products, initiatives, and marketing strategy. Prior to Nvidia, Amulya drove software product marketing and product management for AI software at Intel and other software-centric companies. Rob Callahan is the Chief Product Officer at ConnectTech, where he leverages his 15-year background in engineering and design to drive the company's technical partnerships, manage customer support operations, and actively participate in ConnectTech's events, customer engagement initiatives, and product and business development strategies. Gomanthi Sankar is a seasoned expert in embedded camera solutions with nearly 18 years of experience in embedded edge product development. Currently heading the industrial camera business unit at Econ Systems, he oversees the solution engineering, service engineering, technical support, and field application engineers. First up is Amulya Vishwanath from Nvidia, who will take you through the Nvidia Jetson software stack, a critical component to the development of AMRs. Take it away, Amulya.
Thank you so much, Chris. Hey everyone, Amulya from Nvidia here, excited to be joining my co-presenters. I'll be giving a quick overview of Nvidia's Isaac platform for robotics and how you can leverage this platform for building autonomous mobile robots. Before we start talking more on the robotics side, I wanted to give a brief overview of Nvidia for those who are new to our ecosystem. From gaming GPUs to AI supercomputers, Nvidia's technology revolutionizes industries. Nvidia's computing platform is for the age of AI, where software today can write more software and machines can learn from data. Our products and platforms enable diverse applications such as gaming, visualization, quantum computing, data center, automotive, healthcare, and robotics, to name a few. We have more than 2 million worldwide developers, over 16,000 startups, and over 28,000 enterprise customers that we serve. Autonomous mobile robots, AMRs, are robots that can move and operate in dynamic and complex environments without human intervention. There's a huge industry push, and a typical AMR performs tasks such as picking, sorting, transporting, and delivering goods in warehouse facilities, as an example. You can use these AMRs to improve warehouse efficiency, productivity, safety, and scalability. Remember, these AMRs require advanced capabilities that includes perception, localization, mapping, planning, and coordination, to name a few. NVIDIA Isaac, that I'll be talking more about in the next few slides, is essentially a set of tools and hardware-accelerated packages that allow you to build and deploy AMRs. Now, you might be wondering, why is it challenging to build AMRs? Some of the typical challenges include sensor limitations, where cameras, LiDAR, and other sensors have limitations in range, noise, and interpreting complex scenes. Robots are also required to navigate around moving objects, changing lighting, and unexpected obstacles. Making these robots cost-effective to deploy and maintaining large-scale operations is another huge opportunity and a challenge. So it's really important to build and deploy AMRs that are efficient, highly performant, and intuitive so that humans can interact with and control robots efficiently. The cool thing about leveraging NVIDIA's Isaac platform is that it's your one-stop shop for accessing a comprehensive platform that is backed by an industry ecosystem for building, training, and deploying intelligent robots, including AMRs. The Isaac platform consists of tools, libraries, and hardware-accelerated packages for robot perception, navigation, and control. Typically, you would want to pick one of NVIDIA's pre-trained models so that you could accelerate your time to development and augment it with synthetic data generated in Omniverse Replicator. You could use a tool like NVIDIA Tau to bring your own model or take one of NVIDIA's pre-trained models and achieve a targeted performance on a specific hardware compute platform. Isaac Sim is used to create physically accurate virtual robots in photorealistic environments to develop and test every aspect of a robot's operation. Now, everything else on this site, the main takeaway is that, building AMRs and deploying them has been made easy by NVIDIA's Isaac. And I'll talk a little bit more on the software investments we've been making and also the compute options that we have to offer for our ecosystem. NVIDIA has been making significant investments on the software and compute side of things to enable intelligent robots development and deployment for many years now. NVIDIA's Isaac ROS specifically is a bridge to the most widely used open source framework for robotics development, ROS. Isaac ROS gems are our GPU accelerated modules that provide high performance implementation of common robotics algorithms such as object detection, segmentation, pose estimation, and tracking. A typical AMR robot development demands robust, efficient solutions for perception, navigation, and decision-making in dynamic environments. With the ability to offer powerful AI perception and seamless integration with NVIDIA's hardware, such as Jetson modules, Isaac ROS ensures smooth operation of demanding workloads on resource-constrained AMR platforms. Isaac ROS is a modular and intuitive development environment with a rich ecosystem of tools and packages, allowing one to accelerate development time and reduce the need to reinvent the AMR development wheel. We are backed by a large and active community. Isaac ROS offers ample documentation, tutorials, and helpful forums, which ensures easy access to support and learning resources for our developers. So the main takeaway point here is that Isaac ROS empowers AMR developers to build smarter, faster, and more efficient robots by combining the power of AI, optimized hardware, and a familiar development environment. So remember, Isaac ROS has a plethora of ROS wrappers for NVIDIA hardware such as Jetson, and they can be easily integrated to ROS to enhance the capabilities of AMRs. First, what you see on the right side is a cool option that's offered as a part of NVIDIA ROS. The reason why I say this is because it's so easy for an AMR developer to encounter inefficient hardware acceleration. And there's no point if you're building a highly efficient AMR application and are unable to tap into the most out of hardware acceleration, which is where NVIDIA Isaac Transport for ROS package comes into play. So essentially, this is NVIDIA's implementation of type adaptation and negotiation in ROS2. It's already available. You can access it through NVIDIA's Isaac ROS GitHub. Now, continuing on the hardware investment side of things, you've probably heard of NVIDIA's Jetson, which is our leading robotics computing platform. And the cool thing here is for developers who have multiple performance options. And specifically, what I want to highlight here is that for AMR developers, Jetson AGX Orin, and you'll see that the latest benchmarking numbers are here. I highly encourage you to also take a look at our developer page on all things Jetson, including our latest roadmaps and so on. The main thing here is that developers can choose the right balance between performance and power consumption for their specific needs. So if you're an AMR developer looking to unlock high performance, low power, and cost-effective deployment of AI-enabled AMRs, Jetson AGX Orin is something that you might want to consider. In addition to that, my co-presenters are going to talk more about this, which is the compatibility with the sensors and peripherals and the connectivity aspects as well. Again, the main thing here is that Jetson AI platform is a preferred robotics platform, and it's already compatible with Isaac ROS, and you can unlock seamless hardware acceleration with the help of Isaac platform overall. So in summary, NVIDIA has Isaac robotics platform that is your ecosystem, software, and compute offering combination that allows you to build AMR-based solutions. Our ecosystem is growing rapidly by the day. We have a combination of software partners such as camera, sensor partners, and connectivity partners, and we also have OEM and ODM partners. There's no better way than for you to join an open robotics community that allows you to unlock hardware accelerated robotics abilities along with easy access to seamless and modular packages through Isaac ROS. This combination allows you to tackle key challenges, unlocking faster innovation and performance in your next generation robots. With that, I thank you for the opportunity to share about NVIDIA robotics in today's webinar, and I'll pass over the presentation to Rob. Thank you.
Thanks, Amoya, and welcome everyone. My name is Rob Callahan, and I am the Chief Product Officer here at ConnectTech. We've highlighted the capabilities of the NVIDIA Jetson, as well as the wide array of readily compatible tools and cloud-native building blocks for simulation, integration, and deployment, such as Isaac ROS and Metropolis microservices. Now I'm going to talk a bit more about the hardware needed to take advantage of these tools and capabilities and the challenges you will face when designing a next-generation autonomous system. A fully experienced NVIDIA Jetson partner can certainly help you navigate any challenges you do encounter. Let's go through what these are in a bit more detail. Following Amoya's insightful overview of the NVIDIA Jetson platform, it's clear we're at the cusp of a revolution in autonomous mobility, and NVIDIA Jetson is leading the way. But the question remains, how do you turn this powerful technology into a tangible, operational solution? I'm going to go into a bit more detail and explore the hurdles and solutions when it comes to hardware implementation for autonomous systems. What is the best way to tackle the hardware challenges when developing an autonomous mobile platform? What will stand in our way? Our path is defined by many critical decisions. Sensor selection to meet diverse requirements, the integration of these sensors and systems, and adapting them to the environmental variables of the world around them. As there are many different environments in which an autonomous machine can be deployed, each of them present their own challenges and design considerations when it comes to developing or choosing the right hardware platform. We'll look to briefly address each of these categories, understanding their unique challenges, and deploying solutions to construct a robust autonomous platform. Effective sensor selection lays the foundation for our system's perception. Achieving low latency and high fidelity in our data stream is paramount. We must ensure that our data's integrity remains uncompromised, even over extended distances. I'm going to speak first on vision sensors. As with many autonomous mobility applications, cameras are our starting point. A critical cornerstone for the system's perception, painting a picture of the world around the vehicle, robot, drone, or machine. When it comes to autonomous navigation, object detection, classification, and avoidance, much of this will rely heavily on vision sensor data to make the decisions required when operating. While there are many different ways in which you can bring in video data to the NVIDIA Jetson, in many cases the best way is to bring in raw image data, often providing the lowest latency. One way to bring in this data is directly as MIPI CSI2 data, right from the sensor, a format readily accepted by the Nvidia Jetson hardware. The challenges associated with MIPI CSI2 are often cable length, as it should remain within 30 centimeters of the edge compute, just under 12 inches. For applications or installations where your sensors are going to be in close proximity with the main compute, this becomes the best way to bring in the image data. In many cases, however, sensors will need to be placed further away, and in this case, a serialized version of sending MIPI CSI2 camera data is best utilized. Variants of this architecture include GMSL2 and FPD-Link 3, both of which utilize serializer-deserializer architectures to send the raw data and sensor power over a single wire connection. These methods will still provide a low latency, direct path for the video data while providing you with the flexibility of that extended cable length. Whether it be the front and rear of a vehicle, spanning across ends of a large autonomous industrial or agricultural robot, or ensuring vision capabilities at the base and forks of an autonomous forklift, a serialized protocol will provide the flexibility needed to cover these application requirements and may be best. Depending on your application, other ways to bring in camera data is by utilizing existing standards such as USB and Ethernet. It is important to note that in harsh environments, they may not be the best connected solution. There are of course many other factors to consider when it comes to cameras and their selection, factors such as focal length, image sensor size, and other critical components to vision, and camera selection will be covered later in this webinar. While cameras are often one of the most critical sensors to implement in autonomous mobility applications, vision is just one piece of the puzzle. There are often a number of additional sensors required to ensure you are fully aware of the environment around you, able to provide your system with the data it needs to make proper decisions for mapping, tracking, and mobility. It's not just about what the system sees, it's about a comprehensive awareness of the environment. The thoughtful placement and integration of a variety of sensors will enable our system to navigate and respond with precision, ensuring a fully informed and adaptive operation. These sensors are often a mix of spatial sensors such as 2D and 3D LiDAR, IMU, location-based communication sensors such as GPS, as well as an assortment of proximity, pressure, and other environmental sensors that may be critical to your specific environment or application. Determining the required location of each sensor within your autonomous platform, as well as the best way to interface with each of these additional sensors, will help you finalize the number of connectivity options your end hardware platform will need to run successfully. With the necessary sensors identified, we now face the challenge of connecting them to the brain of our operation, the Nvidia Jetson. This step is crucial, ensuring that the flow of information is continuous and reliable, which is the backbone of our system's functionality. This will likely include camera sensor data over one of the previously mentioned protocols, as well as USB, Ethernet, UART, CAN, and other low-level interfaces to ensure all of the data from each sensor can be processed. If your application utilizes wireless communication protocols to offload data, communicate with other devices, or autonomous platforms, or base stations, you'll also need to ensure you have sufficient transmission of this data by using the correct antenna. Everything from combinational antennas to specialized individual devices for each technology may be required here to ensure no drops in connectivity between the autonomous platform and the intended target wireless devices and systems. The way in which each of these will need to be connected will be determined by your end environment. Connecting Ethernet sensors in a housed Jetson platform versus externally connecting to a system exposed to the outside world present very different challenges. Connector type is often driven by these environmental requirements, which I will touch on a bit later. The physical integration of our sensors, while not the end of our hardware challenges, is certainly a critical checkpoint. The next challenge to consider now that sensor selection and connectivity have been determined is ensuring full integration and access to this critical sensor data within our application. In other words, how do we now clearly communicate with all of these sensors in software and receive the critical data we need? While the connection of all these sensors is akin to teaching our platform to see, software integration is what will allow us to perceive the data provided, make the necessary and critical decisions, and successfully achieve mobile autonomy. As a reference to how you will accomplish this, NVIDIA's Jetpack software suite provides a framework, allowing us to build a cohesive system that can handle the complexities of autonomous operations. This suite includes a low-level board support package reference that can be used as a starting point for development. The next steps will depend on whether you intend to take on all development or collaborate with an NVIDIA hardware or software partner to assist with that development towards rapid deployment. While both options come backed with Nvidia's full software suite, it will determine the amount of effort needed to bring your desired compute and sensor suite to the base required for deployment on an autonomous machine. This development often includes software customization, driver integration, and BSP configuration to ensure full connectivity of all your required peripherals. Now that you've decided on AI compute, chosen the sensors that will best bring in the required data from the outside environment, determined which interfaces are best to ensure reliability, and initiated the development and software integration into the main Jetson software suite, the next major consideration and challenge I'd like to go over is dealing with the environment in which your autonomous solution will operate. As we refine our system, we must also ensure it's built to last, able to endure the rigors of its operating environment. This means designing for thermal efficiency, ruggedization to resist shock and vibration, and protection from the elements, key factors that will determine the longevity and reliability of our system. First, I will speak to thermals. These AI systems will generate heat, and ensuring that they do not reach a temperature at which the processor and your end inference will throttle is critical to autonomous mobility success. Whether your system is being integrated within an enclosure, such as a robotic or automotive platform, if the system is external and exposed to the elements, or if this design must also adhere to application-specific guidelines or industry standards, thermal design is a critical component and consideration for autonomous mobility, hardware design, and selection. Typical cooling solutions implemented on autonomous compute platforms are likely within these categories: active cooling, passive cooling, and thermal transfer. With active cooling, you are introducing a fan or blower, usually in combination with a finned heatsink, which provides the necessary surface area and airflow required to pull the heat away from the main compute, keeping it at a temperature in which it can run efficiently. With a passively cooled solution, the way in which the heat is brought away from the processing remains the same. However, no air is being introduced, thus no additional mechanical components are involved. This is commonly utilized in a system where you have a specific airflow or circulation within the location the system will be installed. In both of these cases, ensuring a consistent ambient temperature range in which the system will be running will be critical to ensure no thermal saturation occurs, which could result in a drop of performance or loss of data. The last option I'll cover is thermal transfer. In this case, the system relies on an external surface to bring heat away from the platform. This could be the outside of the autonomous system itself, connection to a cooling plate, liquid cooling block, or other method of transferring and bringing away the heat somewhere outside of the installed environment. When designing in environments where you can take advantage of moving air, or in tight spaces where the first two methods of thermal relief are not possible, this is often the best way to ensure things run at optimal temperatures in all aspects of your end design environment. Next, I'll talk ruggedization. Different operational fields, from consumer spaces to industrial sites, and even public sector applications, impose their own set of demands. Our system's ruggedization must be tailored to meet these specific challenges, ensuring operational success no matter the external pressures. Like all the environmental aspects I'll be speaking on, ruggedization is closely tied to the best way to ensure proper temperatures of your autonomous design as well. Considerations that need to be made here will depend on the way you will need to have your system installed and your specific application. Whether the system is sitting in a controlled temperature environment, externally accessible and attached to the platform, and if it is exposed to the elements, these will all help determine the level of required ruggedization. If you also must adhere to a set of guidelines and certifications, particularly set for your market or industry, this may create further requirements as to the level of required ruggedization. I've grouped these into three main considerations: commercial, industrial, and what I'll call mill standard. Commercial grade is often acceptable when you have control over your installed environment. The connectors here can often be more of what you may see in a PC: RJ45 connectors for Ethernet, USB Type-C, and often pin headers for some of the additional I/O. The next level is industrial grade. In this case, you are often directly connected to a platform that will experience some level of shock and vibration, in some cases also directly exposed to the outside elements. In this case, you will have to ensure connector selection and internal design considerations are made to adhere to the ratings your hardware will operate in every day. Here, all locking connectors rated for the required level of vibration are utilized to ensure confidence in successful autonomous operation. Lastly, if your system must also meet specific requirements or certifications when it comes to the level of shock and vibration in which the system will need to successfully operate and be tested under, it would meet what I have defined as MIL standard. While not all requirements are in the MIL standard category or market, it's often these standards to withstand high levels of shock and vibration for heavy equipment, aircraft, and large vehicles and equipment that are referenced. In this case, further ruggedization is likely required in the form of a specific selection of external connectors, unit mounting, internal components, and design considerations. When it comes to the Nvidia Jetson, there are available white papers, including one we collaborated with Nvidia on, that go into some of these considerations in more detail. This document is available from the Nvidia Jetson Download Center. Knowing exactly where your end mobile platform is going to be installed, the environment in which it's going to operate in, and the specific requirements and certifications it must meet to be successful in its market are all factors you can use to determine which of these three, or where somewhere in between, may be the best fit when it comes to the level of ruggedization of your platform. Note that while system-level hardware platforms from Nvidia partners often come pre-tested or with pre-certification, your own integration of board-level platforms or system design will have further considerations, all of which you need to account for during the design and testing phase. Finally, protecting the system from invasive dust and moisture is essential. Selecting the appropriate level of ingress protection is more than a detail, it's a safeguard. It ensures that the system remains operational, no matter if it's in a controlled indoor environment or facing the unpredictability of outdoor deployment. Tying in closely with both the ruggedization and thermal considerations, and using the same categorization of commercial, industrial, and MIL standard grade hardware, I will go over the factors that help determine which level of ingress protection you require. There are various ratings, and when it comes to IP rating, in most cases, the commercial grade sits at a level of IP5X. This means while there is a level of dust and moisture protection, both can still enter the system. This is often when it's integrated within a platform enclosure or protected inside housing of an autonomous robot or vehicle. With industrial grade, this is often where you will require an IP67 or similar rating. In this case, you're protected from both water and dust ingress. External connectors on your platform and sensors will need to be chosen specifically so that when connected, they maintain this rating throughout operation. And any of the previously mentioned cooling solutions, whether active, passive, or otherwise, will also need to meet this IP rating. These ratings often hold true for MIL standard or very ruggedized platforms as well, sometimes extending to the requirement of IP68 or IP69K. Knowing what IP rating you will need to meet any predefined market requirements or certifications will contribute as well to the level of ingress protection you will need to ensure you meet in the hardware platform of your autonomous mobile solution. I thought it would be best if I quickly stepped through a few real-world examples, factoring in all the considerations I've just covered. Let's pivot to the field, quite literally, and delve into the world of autonomous agriculture. Picture a vehicle, not just any vehicle, but one that's designed to traverse the unpredictable contours of farmland. It's a system that must not only endure, but thrive under open elements. It will need a level of protection I would consider industrial rated or better, shock and vibration resistance, IP67 or better when it comes to ingress protection and connector selection, and a cooling strategy that meets these ratings and the climate the system will run in. Looking briefly at sensors, while the full suite will of course depend on the end application, you will likely need a range of cameras, 3D sensors such as LiDAR, GNSS location sensors, and wireless connectivity to what will likely be the base station or cloud program gathering data for multiple platforms in the field. Stereo vision or time of flight sensors would be another consideration when it comes to the full sensor suite, providing an extra level of awareness for localization, mapping, and overall operational safety. Given the environment and the length of which many of these sensors will need to sit away from the central compute, a serialized interface such as GMSL2 or FPD-Link 3 may be best. Ethernet can be an additional connectivity option for both cameras and the additional LiDAR and other sensors. Antenna selection, location, and performance will be critical for location data and wireless connectivity. The AGX Orin is likely the best platform in the Jetson family for this application, able to run multiple input streams and models at once. It will help you best utilize and run inference for everything from detection, avoidance, and information gathering at the edge. Imagine now a different scenario, an autonomous robot dedicated to the critical task of last mile delivery. Picture it as the ultimate urban navigator, able to smartly adapt to its environment along its journey. When it comes to the hardware, let's say for this specific example, we're going to integrate our AI Edge platform within the housing of the robot chassis or enclosure itself. This will allow us flexibility when it comes to connectivity of sensors, ruggedization, and connector choices. Given the installation of the hardware will be internally housed, you may look to meet a slightly lower level of shock and vibration than a mill standard type design would require. There are shock and vibration ratings from the IEC, the International Electrotechnical Commission, that may be utilized to ensure a level of ruggedization that can still meet the levels seen in the field. Specific shock mounts or other dampening methods can assist here as well. When it comes to sensors, I believe that again, GMSL2 or FPD-Link 3 may be best for vision, paired with Ethernet for the other LiDAR and external proximity sensors. Note that the environment in which this robot will need to navigate will be much less controlled than a field, so a suite of sensors itself may grow. Again, the AGX Orin is the best compute for this platform, with its ability to handle this growing set of sensor data and the perception needed to run with it. While a full IP67 rating of the system is not required here, you will need to ensure that all externally connected sensors are either properly encapsulated or protected from the elements, or have a rating that allows them to sit standalone. Lights, IR sensors, stereo cameras, or time of flight sensors could all be considerations to ensure efficient operation during the autonomous delivery. We've touched on the key aspects to consider in hardware design for autonomous platforms, with a spotlight on vision as an indispensable element. Yet, there is much more to consider with this key sensor when it comes to perception and autonomy. To dive deeper and sharpen our focus on enhancing vision capabilities, I'd like to welcome Gamathi from Econ Systems, who will take us further into this critical subject.
Thank you, Amulya and Rob, for your valuable information. Let's jump into some colorful stuff, cameras. I'm going to walk you through the role of vision system, what the purpose, before getting into the details. Typical system architecture, then the interesting part, the key features you should know about vision system before choosing the right camera for your application. Then the essential part, software and some case studies. The purpose of vision systems in autonomous mobility, especially applications like delivery robot, warehouse robot, forklifts, autonomous tractors, and cobots, like a robotic arm in the factory automation. The cameras are used for navigation. It could be a robot which follows a line or recognize the barcode to understand the location and navigate, or a stereo camera which can understand the depth to do the visual slam. Then detect, recognize the kind of object. Our cameras are also used for the surrounding system for situational awareness. Here is a quick guide for the system architecture. Choose the kind of processor based on the performance you need. Also, choose the processor based on the number of cameras you would need. MIPI CSI2 is the most widely used and dedicated interface for the camera. You can also use PCI and Jiggy, but MIPI would be more cost effective compared to PCIe and much higher bandwidth compared to Jiggy. Each MIPI lane would support 2.4 gigabits per second. That means roughly you can transfer 1080p around 25 frames per second. AGX Orin, the most powerful processor of Nvidia Jetson series, comes with 16 lanes, which can be divided as 4 4-lane or 6 2-lane interface. So you can have 4 4-lane camera, example 4K at 60 frames per second per interface, or 6 2-lane cameras, which translates into 4K at 30 frames per second camera. Likewise, the Orin NX and Nano can support 3 4-lane cameras or 4 2-lane cameras. But the limitation here is MIPI cable length is limited to roughly 50 to 100 centimeter. You cannot go beyond that. So if you want longer cable, you have to extend the cable length using ZS method like FPD-Link 3 or GMSL. This will allow you to go up to 15 meters. With these additional components, you can extend the cable length from 1 meter to 15 meters. That's the maximum cable length you can use with ZS. It is also possible to increase the number of cameras using the concept called virtual channel. Like I said, the Orin AGX can support 4 lane, but the Unveil platform from Connectech can support 8 GMSL camera. All Nvidia platforms supports this virtual channel concept that can be used for dividing the physical interface into more logical interface. So the bandwidth is going to be the same, but you can divide the physical interface into more logical interface. That's how Unveil can support 8 GMSL camera. So you can connect 8 of our Steadicam 31 camera into Unveil platform. Let's look at the key features of the camera you should know for selecting the ideal camera for your mobility application. Apart from the resolution, there are quite a few key features you should know before you choose the camera. If you are going to use these cameras in indoor applications, you may need certain features. If it is going to be outdoor, that requires certain features. Let's look at the essential features I have listed down here. First thing is shutter type. There are two different shutter types. One is global shutter, another one is rolling shutter. Global shutter cameras are ideal for applications like barcode decoding and depth mapping. The rolling shutter artifact might affect some use cases, but rolling shutter cameras are not only cost effective, it is also more sensitive. That means the performance in low light will be better in rolling shutter cameras compared to global shutter cameras. Another aspect is dynamic range. Rolling shutter sensors are better in dynamic range. So choose the kind of sensor or the kind of shutter type based on the applications. If you are going to use these cameras in an indoor for barcode reading, you should go for a global shutter. If you are going for an outdoor application or even in indoor, if you think the low light performance is essential, consider using rolling shutter. We have a camera called Steadicam 25. It's a global shutter camera with GMSL interface. The same camera is also available in both MIPI and FPD link. This is an ideal camera for an indoor use case. High dynamic range is the key for outdoor application. The unit of dynamic range is in dB. The higher the dynamic range, better it is suited for outdoor use case. Since it's an outdoor application, you cannot control the lighting conditions. The robot may need to go under a tunnel or the sunlight might hit directly into the sensor. You still have to look at the object. Also, the way in which the HDR is implemented on the sensor or on the ISP makes a huge difference. Here we have two different cameras with two different HDR technology. Both of them are made for automotive application. The Steadicam 31 based on Sony Automotive ISX031 sensor has a split pixel technology. You have two different pixels to do the HDR. So the HDR is implemented with split pixel technology, produces lesser motion blur compared to other cameras. On the other hand, the Steadicam 34 is based on onsemi AR0341 sensor, which is again from automotive world, is based on hyperlux technology, which can produce stunning images even when the lighting condition is pretty bad. The 150 dB dynamic range cameras can perform pretty good in all the lighting condition and also in the higher temperature range. Another important feature is synchronization. Synchronization is the key for depth camera. The stereo vision cameras are nothing but two image sensor produces the images exactly at the same time. Since both of them are looking at the same scene, by a triangulation of a particular point from both the sensor will provide us depth. You should also consider the base length depends on the depth range you are looking for. The minimum and maximum distance you want. Based on that, you will have to choose the kind of lens and the base length. The precision of the synchronization has to be precise. So, for depth camera, global shutter sensors are ideal. If you are going to use it in outdoor conditions, still global shutter sensors, the precision level is high, so it is still recommended to use global shutter cameras. But you can also use the rolling shutters, but the depth precision is not going to be precise. We need synchronization for image stitching applications like surround view system. High dynamic range cameras are ideal for this kind of use case. We cannot go for manual exposure as well. We have to go for auto exposure because the lighting condition is unpredictable. So we have to ensure all the cameras are starting the exposure time exactly at the same time, but it has to be still in auto exposure mode. So we align every sensor start of the exposure to the same time, but end of the exposure is going to be depends on the kind of scene it is going to look at. All the cameras from Econ do support synchronization along with auto exposure together. It has been tested on Connectech platform as well. We are also providing stitching algorithm which runs on Nvidia GPU. This is one of those demonstration. Another key element in your vision system is ISP, the image signal processor, that ensures that the camera works on all different lighting conditions. Here on the left is what you usually get it from the sensor, that's a raw bare image, and on the right you are looking at the fully processed image, that's an YUV 422 format image. The right kind of ISP tuning will produce stunning images. Even if you change the lens, you still have to tune the ISP for that. The Nvidia comes with an internal ISP which you can utilize. Also, you can have the ISP on the camera module itself, especially for applications like surround view system where you may need 6 or 8 cameras. It is ideal to go with an external ISP. Another aspect is if you are going to use a Sony sensor like an ISX031 that comes with an built-in ISP. Regular cameras won't be able to read the LED signboards. You need a special feature called LED flicker mitigation. It's a special feature in the sensor. Only automotive sensors supports LED flicker mitigation. If you are using a regular camera to read the signboards, for example, to read the traffic light signal, you may not be able to do that. If you have a camera which supports LED flicker mitigation, you would be able to easily detect the traffic signs and also you would be able to read other LED signs. Only automotive cameras comes with this. Econ's Steadicam 31 or Steadicam 34 supports this feature. This is essential for most of the outdoor applications. Another important aspect is the safety standard. For any outdoor mobility application, you have to ensure that the camera can withstand the wide temperature range, which is minus 40 to 85. Also, you can expect a lot of vibration and shock. So you have to ensure that the camera certified for road vehicle safety standard. For mission critical applications, you don't want to make decisions based on the false data. You have to ensure that the camera is active and also the entire imaging pipeline is proper to make any critical decisions. We got to prevent any major problems. Econ systems provide ways to detect such failures and also we intimate it to the application layer. The health monitoring system which we provides can detect the camera failures and also provides ways to recover. This is essential for outdoor mobility application. All Econ Systems cameras are compatible with ICE across. This will allow you to utilize wide range of perception AI packages from Nvidia. This will reduce the overall development time. You can look at the wide range of cameras from Econ Systems in the below link. Let's look at some use cases. Let's look at the outdoor use cases like autonomous tractors, heavy machineries, or outdoor delivery robot. You would need cameras for surround view system. Also, it can be used for avoiding blind spots for the driver in case it is heavy machinery. Also, you may need a depth camera. For the surround view system, like I mentioned earlier, you would need a high dynamic range cameras like Steadicam 31 is made for outdoor applications. It can be used for any road vehicles, tractors, or even for delivery robot. It can withstand all the environmental conditions, including temperature, vibration, shock, and so on. The rolling shutter cameras comes with 120 dB dynamic range that is ideal for surround view kind of applications. The GMSL2 interface will allow you to take the cable length up to 15 meters. We can also support synchronization with this camera, so you can also do the image stitching. For indoor mobility application, depends on the kind of use case, you can choose the right camera. If you are going to use it in a warehouse robot where you want to detect the barcode and navigate, then you would require a global shutter camera like Steadicam 25. In case if you are going to use it in autonomous forklift, the cameras mainly used for safety or it can be for the autonomous purposes. In those cases, you can either use the global shutter or even you can use the rolling shutter. For depth camera, again you should go for the global shutter camera. That's it from my side. Hope you all enjoyed the session. Over to you, Chris.